we shall be discovering about something, let's say ultraviolet visible spectroscopy today. Fine. And we shall also see what is ultraviolet visible spectroscopy. Up till now, we know the basic concept of spectroscopy. Okay, let's have a quick browse of the basic concept of actually what spectroscopy is. Spectroscopy, as we all know, it is the study wherein electromagnetic radiation is interacting with the matter, and what happens after its interaction with the matter, that is studied by the spectrometer, which is given to us. That means the information is given to us by the spectrometer in the form of a spectrum. And the whole branch which deals with all such kind of study, that is called as spectroscopy. Okay, spectroscopy is based on two things. Either the radiation is absorbed by the system means the matter that we are studying. Okay, so either the radiation is absorbed by the system or it is emitted from the system. Fine. So whenever an electron of a molecule, let's say this is a molecule residing over here, it's an electron of a molecule residing over here in its ground state, that is the E1 energy level. So this electron, the outermost electron, absorbs the radiation, electromagnetic radiation, and when it absorbs the radiation, obviously the energy of the radiation is also absorbed by the electron. So what happens now? The electron carries more energy as compared to what it had earlier. Fine. So when it carries more energy now, it jumps to the higher energy level, next higher energy level, that is the E2 energy level, labeled over here. Fine. So such kind of process in which the electron, the species, is absorbing the electromagnetic radiation and then it is jumping to a higher energy level, the study which we use over here, that is called as absorption spectroscopy. Remember, the absorption of energy is taking place by the species. Okay, absorption spectroscopy, the very common spectroscopies that come under this category, we had already mentioned. Okay, they are UV visible spectroscopy, IR spectroscopy, and so on. Fine. The second is the emission spectroscopy, wherein the reverse process occurs. The electron is sitting in the higher energy level and it comes down to the lower energy level. So in this process, the energy gap which is present between the E1 and E2 energy levels, this energy gap, this excess amount of energy that the electron is now carrying, and when it jumps to the lower energy level, it emits that extra amount of energy. So the spectroscopy technique, it is called as the emission spectroscopy. We get a spectrum out of that movement of electron from higher to the lower energy level. So the technique is called as emission spectroscopy. Okay. Now, up till now we know absorption takes place or emission takes place, and in both the cases we study them separately, absorption spectroscopy and emission spectroscopy. Now let us try to understand the basic instrumentation of these spectroscopic techniques. It is a general instrumentation. It goes for UV visible spectroscopy, or let's say further split it into ultraviolet spectroscopy, visible spectroscopy, IR spectroscopy also. This is the basic instrumentation. The major components of the spectroscope instrument, it is first is the source. What is this source? Source means the source of electromagnetic radiation. Okay, so the source of electromagnetic radiation is one of the component of the instrumentation. Fine. Second is monochromator. Okay, monochromator, and then we have sample, we have a detector and the readout. So these little components are arranged in the same pattern, one after the other. We cannot place sample over here, we cannot place monochromator over here, because that will be of no purpose to us, right? Okay, so what happens? The source of electromagnetic radiation emits or gives us the electromagnetic radiation. Now, these electromagnetic radiations which are coming from the source of EMR, they are polychromatic in nature. Polychromatic means, poly means many. So the waves, they are oriented in all the directions. Okay, there is no particular single one. Fine. So it consists of the entire range. It consists of the entire range of the wavelength of electromagnetic radiation, which are basic components, which are the components of the electromagnetic radiation. Okay, so the source emits the electromagnetic radiation, which is polychromatic in nature, made up of different colors. Okay, it then moves to the through the monochromator. Now what is the purpose of this monochromator? Mono means single. So what does this monochromator do? Monochromator converts the polychromatic radiation into a single one. We'll study how it does it. Okay, so after the monochromator, we get radiation, electromagnetic radiation, which then passes through the sample. Okay, now this is a sample placed over here. The electromagnetic radiation is passing through the sample. Once it has passed through the sample, let's see what happens. Initially, the intensity of the radiation is I naught. Okay. Now, what do you think? If the intensity of the radiation is I naught initially before moving through the sample, so when it has come out of the sample, when it has passed through the sample, will the intensity remain the same? Definitely not. Why? Because the sample will absorb it. Okay, the components of the sample, definitely they are going to absorb a part of the electromagnetic radiation. So automatically the intensity decreases. Okay, which is shown with a thinner arrow over here. Okay, so the radiation passes through the sample. Initially the intensity of the radiation was I naught. Once it gets passed through the sample, the intensity becomes I, which is definitely going to be smaller in value as compared to the I naught. Okay, now this transmitted radiation passes through the detector. The detector detects it and then reads it. Okay, and then finally we get the readout over there as the result. Fine. This is one of the pictorial representation wherein it is the same process has been shown with means of the different components in the figure. This is a beam source over here. That is a source we had talked about it here. Okay, polychromatic in nature, made up of different colors. Okay, different colors means all the wavelengths. Okay, incident radiation, and then monochromator is there. Okay, then it passes through the sample. These are the molecules of the substance which are taken as a sample. Electron is sitting over here in its ground state, or let's say the lower energy state, lower energy level. It absorbs energy and then jumps to the higher energy level. Okay, so now it is here. So what is happening? Absorption is happening. So under what category this particular process comes in? Absorption spectroscopy. Right now, when this transition has taken place, this transition is detected by the detector through the transmitted light, and the detector gives the spectrum. It reads, and then we get the spectrum through the readout to the monitor. Fine. The spectrum, as I told you, it is a simple graph between the intensity of the light, okay, intensity of the light and the wavelength or the frequency. Okay, fine. Now, we are going to discuss each component of the instrument separately. The first component was the source of electromagnetic radiation. Let's see what are the sources. The source of electromagnetic radiation. Now, depending upon the type of spectroscopy that we need to study, there are different sources of EMR. For example, if I want to study my sample in the ultraviolet radiation part, ultraviolet radiation means below 400 nanometers, right? So if I want the radiation only in this particular ultraviolet range, then I don't need to go through all these types of radiations. I simply need a source which can provide me with the wavelength range from 150 to, or let's say 160 to 400 nanometers. Okay, so for that sake, the source of radiation is hydrogen deuterium discharge lamp. Okay, so for ultraviolet part of the radiation, in the spectrometer we use the source, which is actually a hydrogen deuterium lamp, and it provides the wavelength in the range of 160 to 375 nanometers, that is below 400 nanometers, which is actually the ultraviolet part of the radiation. Fine. If I want to study my sample in the visible part of the EMR, suppose my sample is colored, so there is no use in having the ultraviolet source. Then why should I spend more for that? I go for the visible part of the radiation, and the spectroscopy, it is called as visible spectroscopy. For visible spectroscopy, that means for the visible part of the radiation, okay, electromagnetic radiation, in other words, wavelength above 400 nanometers and up till 800 nanometers. Okay, fine. So for visible spectroscopy, we use the source of radiation as tungsten filament lamp. Okay, so the tungsten filament lamp is used for visible spectroscopy. And remember, in the UV visible spectrophotometer that we use, there is a switch which asks you before starting the software whether you want to use the UV part or the visible part. So if you want to use the UV part also, you switch on that UV lamp. So whenever you put it on, the hydrogen deuterium discharge lamp is on, right? But if I don't need the ultraviolet part of the radiation, I don't put it on. I'm simply put on the switch for the visible part. Okay, so in that case, hydrogen deuterium lamp will not be functional, will not be on, but instead it will be tungsten filament lamp. So actually both the lamps are provided in the same instrument. Therefore they ask you. Okay, so and for IR spectroscopy, we have different types of sources of radiation. Like for example, we have Nernst glower, incandescent lamp, tungsten lamp, Glober source, nichrome wire and Nernst glower are usually used for the infrared spectroscopy. So these are the different sources of electromagnetic radiation which are basically asked anywhere you attempt any type of exam. These sources can be asked. Okay. Second is the wavelength selector or the monochromator. The second component of the instrumentation, first we have already discussed now the source of radiation. For ultraviolet is different, why visible is different, and for infrared spectroscopy it is a different source, all the three cases. Okay, now we shall discuss the second part of the instrumentation, the second component of the instrumentation, that is the monochromator. Monochromator is also called as wavelength selector. As I had told you, from the source of radiation, the polychromatic waves come, okay, or the polychromatic radiation, they come out of the source of EMR. Now this I don't require the entire wavelength range of the EMR. I simply require the, let's say, the yellow part, or let's say the blue part, fine, or let's say the ultraviolet region in a particular wavelength range. So how do I do that? How do I filter that? Okay, for that sake a monochromator is used. So what happens, the polychromatic radiation, it enters the monochromator. See, a prism can act as a monochromator, or these gratings can also act as monochromator. Fine. So the white light is coming over here. That is the entire electromagnetic radiation, which is polychromatic in nature. It is entering the prism. Similarly, it is striking over the diffraction grating at a particular angle. Fine. And after passing through it in the prism also, we get different colors. Yes. So a monochromator, actually what does it do? It splits the beam. It splits the beam of white light coming. See here also, this grating is splitting the beam of white light which is striking on its surface, right? So a monochromator splits the beam and then collimates it. Collimates means it arranges them parallel to each other. Parallelly it arranges the components of the beam. Okay, so it splits the beam, collimates it, and after it gets striked at a particular angle, fine, and actually the beam is split into its component colors, or if it is not the visible part, we say it is split into its component different wavelengths. Okay, so the various types of monochromators, it can be prism, it can be gratings, diffraction gratings as it is shown over here, it can be filters also. After it has been split up and collimated, there is a slit which is movable actually. So if I want to have this wavelength range, I put a slit, the instrument moves this slit in such a manner that it gives out the this part of the electromagnetic radiation. Okay, now these prisms can be made up of, usually they are made up of, in fact, potassium bromide, sodium chloride, or cesium iodide, whereas the filters are usually made up of lithium fluoride, right? So this is the second component of the instrumentation, that is the monochromator, also known as wavelength selector. What does it do? It converts the polychromatic radiation into monochromatic radiation. How does it do that? It splits the beam into its different wavelengths, okay, and then collimates them. Fine. The third section of the instrumentation is the sample holder or the cuvette. Very interesting actually. Okay, for UV visible spectroscopy, we have a special type of sample holder which actually looks like these small tubes. Okay, as you can see, they are transparent in nature. Fine. They can be made up of quartz or fused silica, in fact. Okay, they can be made up of quartz, they can be made up of glass, and also now the plastic cuvettes are also available. Now, why these three different kinds? In fact, quartz is the expensive out of these three categories. Okay, actually what happens, quartz can work, in fact, in the ultraviolet part of the radiation as well as in the visible part of the radiation. See, the function of the cuvette should not undergo absorption of light. Why? If the cuvette is absorbing the electromagnetic radiation, then how will I come to know that how much radiation has been absorbed by my sample which is inside the cuvette? So the cuvette should not show any absorption in that particular range which I am studying. Okay, and it should be functional also in that particular range. Obviously, that is the criteria how we decide which kind of cuvette we can use for our study. Okay, so the quartz or the fused silica cuvettes are used in the ultraviolet region of the electromagnetic radiation. Okay, in other words, the quartz or the fused silica cuvette is used in the ultraviolet spectroscopy. Although quartz can also function well in the visible part also, in the visible spectroscopy also, but actually it is costly. Okay, fine. The glass cuvettes can be used, or in fact the glass and the plastic cuvettes are used in the visible part of the radiation. In the visible spectroscopy, the glass or the plastic cuvettes are used. Now the question arises, why can't we use glass cuvettes in the ultraviolet region when they are less costlier than the quartz? Okay, why? Because glass cuvettes are not actually used in the ultraviolet part of the radiation, because glass itself absorbs the wavelength which is lesser than 350 nanometers. 350 nanometers means in the ultraviolet region. Okay, so glass itself shows absorption, and plastic also itself shows absorption in the wavelength lesser than 400 nanometers, that is the ultraviolet part of the radiation. Therefore we do not use these two materials for the ultraviolet spectroscopy. Okay, now this was about the UV visible and UV visible spectroscopy. Next is the infrared spectroscopy. Infrared, that is IR spectroscopy, you can have solid samples. For UV visible spectroscopy, we usually have the liquid samples like these, as shown, colored and colorless samples shown in the cuvettes. They're different colors. Okay, but for IR spectroscopy, you can have a solid sample. So whenever you have a solid sample, you prepare those samples. Example, using a pressed pellet technique, in which the sample is taken, it is mixed with KBr, fine. Usually 1:3 ratio is taken of sample and KBr. You mix them properly using a mortar and pestle, fine. So you mix them properly using mortar and pestle, and that mortar and pestle is made up of a special substance that is called as agate. Okay, so agate, mortar and pestle is used actually for grinding the sample, converting into fine powder, very fine tiny particles, okay, of the sample. So you mix them, you mix the sample with KBr usually, and then what we do, we take the mixture, introduce it into a dye, which actually is a very small instrument that exerts a very high pressure on the mixture that you have prepared, and the pressure is so high that the mixture, it binds together, becomes a compact, very thin tablet like of a structure. Okay, and those structures that you have prepared after pressing at a very high pressure, they are called as pellets, and hence the technique is pressed pellet technique. Fine, this is the case wherein the powder sample is there. Okay, and you can prepare pellets. Another form can be in the form of solid films also, like I can prepare a film of my sample, or let's say my sample is such that a film can be prepared. For example, polymers you use, you can prepare film of the polymers. But if I my sample is clay, normal clay that we have around us, or I cannot prepare a film of that clay. Okay, for that sake I need to go for the pellet, pressed pellet technique. But if the film can be prepared, then you can have a solid film technique also. Okay, for the sample preparation. Okay, so for liquid samples in IR spectroscopy, that's very simple. The samples are held using a liquid sample cell, which is actually made up of alkali halides. Okay, now aqueous samples cannot be used with the liquid sample cell. Why? Because it is made up of alkali halides. Okay, and if the aqueous solvents are used, they will dissolve this alkali halide. They gets dissolved in the aqueous medium. So only the organic solvents are used over in those cases for the samples, wherein the samples are liquid in state to be studied by the IR spectroscopy. Okay, for the gaseous samples, the sampling is just similar as we have talked about liquids. Okay, so this was the third component of the instrumentation, that is the sample holder or the cuvette. These tubular apparatus kind of a thing that you see over here, they are called as cuvettes. Okay, fine. Next component of the instrumentation is the detectors. Now what does the detector do? Remember, the incident light was passing through the sample, intensity was I naught. When it has passed through the sample, it comes out of the sample, the intensity has changed now, it is I. Okay, capital I. This process, this change in intensity, it then moves to the radiation moves to the detector, which then studies the transmitted light from the sample. How does it do? It absorbs the energy of photons, it absorbs that radiation passing which has come to it after passing through the sample, and then it converts that radiation into a measurable quantity. It can be a change in thermal properties, or let's say the change in temperature. It can be a change in current also, likewise. So that is the function of the detector, converts the radiation and gives the information. Fine. UV visible spectroscopy purposes, that is for UV visible spectroscopy, the commonly used detector is photomultiplier tube, PMT, capital P, capital M, capital T. You must have heard about this terminology. Okay, so PMT or the photomultiplier tube is used for UV visible spectroscopy. For IR spectroscopy, we can have thermocouples. Very simple. Actually, these are the junction which are made up of the different metals, two different metals. They form a thermocouple. Pyroelectric detectors. Okay, or it can be photoconducting detectors, which actually consist of a film of semiconducting material. So it is a photoconducting detectors. Okay, these three can be used for IR spectroscopy. Now the last component of the instrumentation is the amplifier. My detector is detecting what change has taken place in the electromagnetic radiation after it has passed through the sample. But the result that we obtain from the detector, it is so small in magnitude that it cannot be easily readable for an observer or for the experimenter. So what happens? Those signals, they then pass through the amplifier. Okay, amplifier amplifies the signals which are obtained from the detector, so that it is measurable, so that it becomes a measurable quantity. Okay, it takes in the signal from the circuit to produce an output signal, which is actually the several orders of the magnitude than what it has received, than what the amplifier has received from the detector. Okay, so basically it amplifies the signals that it receives from the detector and then which are displayed.